Well, on.
Let's take a look.
Like,
Uh, do you want to share something?
something to share, but I think Jayanta could provide some context.
Okay. Mm-hmm. Mm-hmm. This is for the basement telluride. Okay. Okay. Copper titanium telluride. So the copper is disordered, right? Let's look at the band structure. You send me the draft or something, right, Jayanta? So the folder you shared, I didn't open it. Oh, this is also germanium telluride. Okay. So do you have anything? Show me what you have so far for copper. I think you shared it in the subgroup meeting, right, on Tuesday. Can you share it again? Yeah, let's open it again. What's the problem? Let's take a look. So Partha replied, by the way, your germanium telluride paper, he's doing final edits. He will add you also as joint first author. I asked him to do that. Yeah, yeah, I think were you worried that he will not? Really? I mean, mm, mm, I see. I see. He said, yeah, I will put Jayant as joint first author according to your suggestions. I didn't think they would not stabilize the phase. So I wrote I think without this, not possible, without the thermoelectric, yeah, exactly. Exactly, right? So I mean, that's what I said. I see. Yeah, so I think it's only fair. Yeah, yeah. So I think he agreed. He will finalize it. I mean, it doesn't matter. I trust. No worries. Before I share something, yeah. hmm Mm. Okay. Did you already set up the DJS in their lab? I thought, no, they don't want to do it, or what is it? Okay. Oh, okay, okay, okay. Yeah, I mean, if I get a chance, but if he gets a chance to talk, he can just include me as a some collaborator, overseas collaborator, if that helps. You can ask him that he can do that. I mean, it'll be good for them to try. Okay. Anyway. Mhm. 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 Yeah. Did you talk to Savia or? Okay. Yes, Andy, what I was suggesting here is that so only in the presence of extra titanium is
Mhm.
are they able to stabilize the pure phase.
Yeah, I was trying
Okay.
to rationalize it in my head, and then it seems like we're moving with the extra titanium, we're moving it onto the line, like between the copper titanium telluride and then pure copper, and then like the one of the decomposition phases will not be copper telluride. So that was my rationalization, but also like that doesn't like explain like why the 414 phase forms.
Yeah, so I mean, they have these chemical potential diagrams, right? Um, I don't know what. I mean, I know they do it for defect diagrams.
The chemical potential is kind of
Let me show
it's
you.
kind of included in the calculation for formation energy. So
Mm.
I was like wondering what kind of a deconvolution would it involve. I've never seen some kind of diagram like that before.
Yeah, I mean, it's. I remember seeing these plots by Sabrine. Okay, let's see if I can find her pieces. Give me a second. This is a long time ago. Mm, I don't seem to have a copy of this right now. But they run these. So for a defect to form, what they can consider is like each element can have higher or lower chemical potential. Okay, so in the presence of extra titanium, that means that it's excess titanium. What is the propensity of the formation energy to form under excess or lack of titanium, something like this. So you could then guess, is copper telluride has a less chance to form compared to copper titanium telluride in the presence of extra titanium. That would prove it, right?
This sounds like it's a formation of a defect, but at the same time, this is like a whole phase that is precipitated out of the
Yeah.
mix.
So
Yeah,
that's why I only remember formation of defects, chemical potential diagrams are quite,
yeah,
but I don't
yeah.
know about full phase.
Um,
This is why I wanted to ask what's his name, Savia, to look at it, but maybe he knows how to do this. But he thinks too much about defects.
you could like have an defect analog of a copper telluride base, like kind of a
Yeah,
yeah.
that
But
would really add
yeah.
something. I cannot find these figures. I don't know why. Wait
It's
a
like a
second.
transition level diagram.
Is it? No, it's not the transition diagram because that's just a. Let me see. Give me a minute here. Formation of defects, excess or lack of an element. Generally, David Scanlon's implemented. Hmm, I don't know. I don't know how to find this. Yeah, I mean, but if we are able to use that sort of analogy, what that'll do is, Jayanta, it'll help us show that under excess titanium, I don't know how they define it exactly with DFT, but it would say like under the presence of excess titanium, the chance of forming copper telluride with the formation energy of copper telluride under excess titanium should be higher than that of copper 4 titanium telluride, right? And that shows that energetically it's favorable to form copper 4 titanium telluride. I just don't know how they perform those calculations. This is what I'm not sure. This is why you should talk to Xavier about this. I will think about it a little bit after our meeting, but I don't have an answer right now. Okay. But this is not the main. Let's look at the band structure, right? Uh-huh. Mhm. This is very nice, right? This kind of analysis is not done before. Can you go back? So the structure solving, what is there a problem or it looks very clean? Everything looks good. Mhm. Hey, so what is this diagram on the right? Can you walk us through it? Different Wyckoff sites. Mm-hmm. Okay. Mm-hmm. 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 Where is this diagram coming from? The group subgroup diagram? But I mean, it's done. It's so they've solved. They actually have the experimental data for different structures at different temperatures, and then they fit it, and then they show the transition from the cubic to the. Is that what's going on? Mm-hmm. 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 4E site becomes a 16E, and then 2113E, so symmetry reduces. I see there's some sort of splitting of the symmetry for the 4E side. So the 4E side 3 mirror, it goes into multiple sites with some lower symmetry from it. Mm-hmm. 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 I see. So, I mean, I think this is generally true, right? For many compounds where, it goes towards a high symmetry structure, and that's because of like you can imagine like as temperature increases, all the sites get occupied with equal probability, and it goes into 25% some occupancy. Okay, that's okay. That's quite clear. Okay. So at this point, can you go back to slide? What did exactly did you calculate, Andy? Can you walk me through the steps? Sorry, I think you're muted. There was some background, so I muted you. Sorry.
Sorry. So during you started like with generating like 400 virtual cells with those,
Okay.
right? You can exactly like assess like how many different coordination environments
Mm-hmm.
that tellurium has like in relation to titanium and copper. So each tellurium definitely is bonded to one titanium, and then
Mm-hmm.
the copper is variable. Uh, maybe I should, maybe I could share it because I have like some details to
Yeah.
also,
Yeah.
yeah.
Can you stop sharing? Yeah.
I'll start like another sharing on top of this.
1 sec, Andy, 1 sec. Yeah.
Okay.
Mm-hmm. 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 But I mean, if you look at, if you draw like a vertical line here, let's say 200, then the ratio of these bonded sites is not changing that much, right? Mhm. Most of it. Okay, I see.
Do you have a like lower copper in there? Then the tellurium like lone pairs become like more, and then that has some impact on the thermal conductivity.
Mm.
Yeah. Sharing, yeah. Okay, yeah. So this is like the electron localization. Like from a single cell, I pick one that has like all the different. I mean the range of different coordinations that are possible. So uh, tellurium, copper, titanium. So tellurium is 3 copper, 4 copper, 5 copper, and 6 copper. So
I see.
the electron localization function is the calculation of the likelihood of a electron pair occurring at a site. It's like a probability quantity. So the less copper that this particular atom connects to, then the more likely that you see
Mhm.
a Te like 5s2 lone pair. And then
Mm.
this is accessible like not from the disordered like source cell, but like have to
Mhm.
like elucidate the virtual cells, and then like it count like each counts like based on the titanium, like what kind of coordinations they are. And then like
So
this
one
is
question is, when they say this thing, there's a word that's used called stereochemically active lone pair. Do you know what does that mean?
stereochemically active nodes.
Yeah. Look into this. It's important because that's the time when I think it basically means that if the lone pair is active, it changes the bonding of the cell or something like this. Okay. Otherwise, the structure won't change. I think here you can basically call it stereochemically active because, I mean, I don't know what's the cause and effect, right? But
Yeah, I don't know.
basically, when your lone pairs are causing, I don't know. The question is, if you have the tellurium 6s lone pairs, is
Hmm.
that responsible for only 3 copper bonding to and or you see what I mean? Like, I just don't know if that's the case or not. So you can look into that literature a little bit because
Um,
you could flip the question the other way, right? Why is it that at low temperature, I mean, it kind of makes sense intuitively, but why is it at low temperature tellurium only bonds to 3 coppers, right? And it's got to do with the lone pair, right? Because it probably acts as a repulsive orbital that doesn't allow bonding to occur. Yeah, and then at higher temperatures, that is broken somehow, and you're able to get to, I don't know. Uh, yeah, it's not clear in my head.
mm,
Mm-hmm. 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 I okay. Okay. Mm-hmm. Okay.
Think about it as like kind of here's a the expression of entropy in higher temperatures means that like the four different sites in a lower symmetry in rhombohedral becomes like
Mm-hmm.
same as each other and
Mm-hmm.
resulting in a cubic symmetry.
Mm-hmm. Okay.
But well, when I did this, I'm like the cause and effect is just like I was working with the rebelt refinement cells that
Mm-hmm.
Jayanta provided, and I think okay, this is the ground truth, like which is the experiment, and then like see
Mm-hmm.
what kind of thing I can say like based on the tellurium 5s2 lone pairs that I can get from the so turns out it's quite a lot.
Okay. It's quite nice actually. The analysis is quite good, right? So I
Yeah,
think next to this figure, Jayanta, and the paper, you need to add these because I don't know what T to 4 copper, T to 3 copper, T to 5 and 6 copper mean, right? But with this picture, it's very clear. So you just put this next to the yeah, so that people understand. I think it's important. Label the atoms and stuff like that.
yeah, would be helpful. I mean, like to try to. I was like thinking like just like cut these out and put it in the picture, but then the six copper, like where do you put them? And it's a small issue, but
Yeah,
no solutions yet.
yeah.
Would you like to move on to the band structure?
Yeah, let's look at the band structure.
Okay, this one is I spent a lot of weeks just to make easy unfold work. So we've heard from Sabrine regarding easy unfold. Xavier's dabble with it. But none of us so far has actually like used it in actual work. So here I come
Mm-hmm.
do it on Janta's
Mm-hmm.
structure. I think this is the lower temperature phase, which
Yeah.
is
Mm-hmm.
like the rhombohedral phase, and it works. And it's just like
Mm-hmm.
I got it to work at the PBE level. The challenges is that where you want to like make it a little bit more like precise.
Mm-hmm.
Like say like maybe hopefully like the HSE or spin orbit coupling will give you a more like accurate description of the band gap.
Mm-hmm.
Then I think like it doesn't say in easy unfold like documentation, but spin orbit coupling just throws it off. So I have to start over again. And HSC I think
Mm-hmm.
has some like wrestling
Mm-hmm.
with the software also, and I think like it wasn't doable like based on like how big the cell is.
Mm-hmm.
So
Yeah, so I
consulting
mean,
with
yeah. So yeah, go ahead. Go ahead. Why don't you finish?
so after a few like back and forth with like with ChatGPT, like it suggested something called a scissors operator, which is just like
Mm-hmm.
um because like what I've experienced before in a hybrid functional is that the conduction band just gets moved up in concert.
Yeah, right.
Doesn't like change the relative like
Yeah.
location of the band within the CP, so you can safely use like something called a scissors operator, which is just um taking this section of the graph and then move it upwards.
Yeah. I mean,
Yeah,
you don't need to. So I think what you could do is just I mean, it's up to you, right? If you're confident with this, can we validate? That's even better. But at the very minimum, at the PB level, what is the two things that we want from this band structure, right? Two things we want is one, it shows that there's a small band gap. Anyway, DFT band gap is typically um, underreported. Okay, there's a
yeah, it's underreported.
yeah, it's the actual band gap, quasi-particle band gap in real materials should be higher than this. Okay, so this is sort of the lower limit. At the gamma point, you have a direct gap.
Yeah, gamma direct gap at a gamma point.
Yeah, and the gamma is like 0.675 or 6 eV, whatever, right?
Yeah.
So firstly, you can point out that in the discussion. Now, for the okay, before I move on, firstly, this lower temperature phase, why is it all fuzzy here?
It's fuzzy because it's an unfolded bank structure. Like it's
Okay.
based on like one particular virtual cell.
Mm-hmm.
So it's taken where we take it for granted that it'll be fuzzy a bit because it's a kind of a like a primitive cell reciprocal space like high symmetry vectors that are like mapped onto a supercell.
Okay.
And then there's a bit of uncertainty because like this is like one particular expression.
Will there be a problem if you put this band structure like this in a paper?
I don't think so at all because I think it's understood that it will look like this.
Okay.
Probably it'd be strange if it like looks clean.
Okay. Okay. So I think it's good to put this in. and say,
Yeah.
hey, solve the band structure, including the disorder, by using a virtual cell. I think Andy knows what to write here. His tool is very good at this. This is why we got him to do this for us. Okay.
I'm I learned
But,
this and only really got this to work like yesterday.
oh, okay. So you did
Before that
that.
was yeah.
Okay. I was kind of expecting they already did. So yeah, that's nice. This is really good. You could even take the high temperature cubic phase. What temperature is it to convert to cubic? 320 Kelvin. Yeah, so we should do the cubic phase, right, Andy? And
Yeah.
just do the easy unfold. And then I think most of the transport analysis will be done in the cubic phase. So
So yeah.
yeah, so the next step is, so you do low temperature, high temperature, and then so one thing is there's a gap, and then you look at the cubic and see, does the gap change or what happens? Okay, that's this. You have to look at that. And the second thing for the cubic phase, and most likely for the cubic phase, would be look at the effective masses.
So something
What?
like curvature.
Yeah, exactly. Secondary.
The yeah.
So this is secondary to the energy, respect to K, right? And this is Seebeck is positive, right, Jayanta? Oof, so this is a bit tricky because here it looks like the Fermi level is close to the conduction band.
Yeah, I think this is something I hope to fix with the scissors.
Okay, okay. Take a look at it. But if the conduction band moves up, yeah, I don't know. So you need to check. This is something. But I
Mm,
think maybe you focus on the cubic phase. I think the low temperature phase is not that important because most of the transport is high temperature.
yeah.
And higher symmetry should be make easy to unfold because the number of symmetry points in that phase should be fewer, right? So even this looks pretty clean. So I think in the high temperature phase be even easier, right? So I would
Yep.
focus on the cubic phase, but extract exactly this band structure, and then at critical points, you would extract two things. One is the band gap, which I expect to be low band gap. I think in the paper they predicted it to be 0.4 eV, right, Jayanta? But that's slide one. But is that for the low temperature phase or the high temperature phase? Okay. Can you go to slide one? Yeah, what's the band
Something
gap?
like 0.4.
Yeah, exactly. That's exactly what they
0.4, yeah.
reported. So this is very, very good, right? Where is the lone pair? Typically, the lone pair shows
Mm,
up somewhere, right? Like, is it the tellurium P? So the green line, that's the lone pair or something?
it should be like tellurium S. And then there's
Sorry, on the
if
P.
that's the case, it would be a core state. Then
Yeah, yeah. Sorry. I'm tellurium S. Look for the tellurium S. If you can look for it and see where it shows up, that'll be useful. If it's in the band, then it's hybridized, which I think also adds to your bonding picture, right? But like the other thing that I remember again from a few years back is that the S, the lone pair NS2 are somewhere, I can't draw here. I can draw. It's somewhere in the middle, like it's a small density states here. That's very interesting. That results in low thermal conductivity because it's basically not, the bond is not hybridizing with anything else. And that's basically, if you imagine a structure, electrons are completely unbonded, and that results in a huge anharmonicity, and that gives you low thermal conductivity. But I don't think that's the case here, right? I don't see anything
mm.
specific. But just try to pay attention to the NS2, whichever 6x2 or something. For that,
Mm.
yeah, look for the 6x2 in the partial density stage to see where it is. Okay.
Yeah, I was thinking if it's like really like if it's a core state, like treated as a core state, it could be like somewhere very far on the left side. So it absolutely get cropped out.
Why would it be the course? It should not be the course.
Oh, it's non-bonding also.
It's non-bonding. I don't know enough. I mean, I think this is how you got to check like Aaron Walsh's papers. He's done a lot of work on lone pairs. Okay. But I think it's related to this thing I was talking about earlier. Like, is it stereochemically active or not? There's a whole body of literature we can find it, so you can look into this. Okay. But yeah, so I think the high temperature phase cubic, you look at the effective masses for the P type side. Okay, hopefully it's a, the one big problem is if it looks like a conduction band, then they will ask the question like, why is your material P type? right? This is going to be a problem. Is it B? Wait, so let me see. Let me see. So this is titanium and tellurium. What is this color?
This is copper D.
Huh? Copper D. Which are the bonding, which is the anti-bonding
This
orbital?
side is bonding.
Which side?
Left side should be bonding.
So this is the valence band, right?
Yeah,
The conduction band.
yeah.
How come the Fermi level here is close to the p side? This is correct, but then doesn't match with the unfolding band, isn't it?
Mm, yeah, I think like unfolding band they is the I think it's the from the fact that like Fermi energy, like where do the DFT like people put Fermi energy is quite arbitrary.
Mm-hmm.
Like by default it's something like a top edge of the valence band.
Mm.
But like there could be other ways of like calculating it. That means like different ways of cracking the DFT results could result in different levels of Fermi.
Okay, but we need an answer. We need the Fermi level to be next to the conduction band, valence band.
Yeah.
What is the Seebeck value, Jayanta? 10, 20? Yes, it's definitely inside the band on the P side. Positive, right? Yeah, so why don't you look into that, Andy, a little bit? I don't know what knobs you have to tune this, but the Fermi level should be in the valence band.
Mm.
Otherwise we'll have trouble with explaining why the band structure is correct. But anyway, so at the end of the day, what you have to do is, I think the only input you need from here, the agenda, is your effective masses, right? Which I think you have from the previous band structure. Just validate that and use the new numbers to calculate the transport. That's it. Yeah. I mean, since you have this, Andy, once the band structure is done, this is a supercell, right?
These are supercells.
Yeah. So then this AM set calculation I think is not easy, not trivial to do on supercells. Again, Sabrine did it. So I don't know how valuable it is. I think let's go back to your data, Jayanta.
Stop share.
Go to transport. So I think this part is okay, right? Everything is clear. Mm. Yeah, use that data. That's it, basically. So get to some one good transport data, one or two good transport data, cutting without the oil, and let's hope to get some. I mean, the conductivity is low, you know, which is not great. So thermal conductivity is quite low, which is as expected, right? Yeah, I mean, the paper focuses on phase purity, right? And that's the key. Yeah. Mhm. So once you've solved the structure, right, Andy, and you have the supercell, Nongwei is back next week. Can you ask him to do the auto kappa on that cell? I think you're muted again.
Muted again.
Yeah, are you aware of this auto kappa?
Auto kappa. No.
Okay, auto kappa is like automatic thermal conductivity calculation. So what he can do is
Nice.
once you have the solved supercell, the cubic, you just take that supercell, give him the CIF file, and Nongwei should be able to run the thermal conductivity for you. So we can overlay the thermal conductivity, temperature dependent. Then we
Mm.
put it in there. When they analyze it, there's a lot of stuff that it spits out, like a phonon, blah, blah, it relaxes it. There's a whole bunch of stuff available in there, which will complement the electronic band structure calculation. Okay, so that's the next step because I think we don't want to focus so much on thermoelectrics. If you, I mean, I remember I asked you if you're going to try to dope it, right? Did it work, Jayanta, with silver or additional or less copper? I think. Oh, okay. It worked, right? Amazing. Okay. But copper, this is quite nice, right? You already have a order of magnitude change in K concentration. What is this H1C1? Not repeatable data, is it? Okay, okay. So we don't know if it's stable or not. So you need to get stable data first. Mm-hmm. I see. Yes, actually, our intrinsic thermal conductivity is basically here. This increases thermal conductivity, or maybe because of the vitamin Franz law or something. No, if it's de-doping, how come the conductivity increases? This is a bit odd, right? Okay, okay. I think yeah, you need to redo this because this doesn't make sense, right? If you're because as you okay, as you go 3.8, oh, it's the other side, 4.2, 4.4. So if you do here, then the conductivity is increasing, right? So let's say this is within error bar. These two are within error bar. I don't know if it's correct or wrong. Let's say you have one line here somewhere. Okay. So higher than 4, your electrical conductivity should increase. You see? So K electronic is probably increasing. I know, I know. Oh, it's just K lattice. Oh, okay. I see, I see, I see. That doesn't make sense. K lattice should go down. So I think you'll need to work a little bit harder on the transport data. Yeah, take your pure sample and just get repeatable data first, right? And don't work on doping for that for now. Okay. Yeah, but I think it's coming together nicely. So Andy, I think the band structure helps. Focus on the cubic phase. Try to make sure that the Seebeck coefficient you see is positive, means that the Fermi level should be near the conduction, sorry, near the valence band, and then pass the CIF file of some structure to Nongwei. He can do the auto kappa calculation for us.
Okay.
Meanwhile, Jayanta, you need to repeat the synthesis and try to cut it cleanly so you can get clean data. But nominally, you see, what's not good is I don't know why your conductivity is so low. Yeah, I would expect it to be much higher, man. What is the effective mass approximately? Do you know? The old band structure calculation. It's relatively high. So the conductivity, the mobility might not be great. Okay, so which is why your conductivity is not great. Yeah, so it's not a good thermoelectric probably because it's the effective mass is too high. Hmm. Yes, just focus on thermal conductivity. You can make a nice story out of it. And mhm, yeah. I mean, it's if you go back to your temperature dependent XRD, go back to your data. At what point does the copper telluride start to form with excess titanium? Yeah, so you go till 460 first, you collect the ton transport data. But for thermoelectrics, you don't need pure phase. So I think you kind of want to say, hey, the synthesis technique gets you pure phase. So we're doing the pure phase study. But by the way, we can also go to high temperatures, you get better performance because, of course, there's phase separation, but that's not a problem with thermoelectrics. I don't know. We'll have to see first the data, then we can figure out how to reverse spin it, right? Mm. Yeah, it should work. Yeah, that's not good practice. I think you need 95, greater than 95 is okay because thermal conductivity error is like 5 to 10%. And I think greater than 98, 99 is the best. 90 is not good. Okay. Okay. Great. I think it's coming along nicely. So this will come through AutoCapper. So once Andy sends the structure to Norway, he will put it on the supercomputer. In a week, you'll get the result. Okay. So please make sure you do that. But don't bug him for now, man. He's like taking a break after his PhD defense. He's he's like he's this weekend he's going to be in Malaysia. He's back on Tuesday. He needs to answer the rebuttal of his paper. I just had a meeting with him this morning. It's very important. But you can send it, you can still bug him on Tuesday or Wednesday and say, and Andy, you can tell him sorry. Kedar says sorry, but just run this one compound through AutoCappa. He'll be able to do it. He doesn't have to do any work, right? Just put it on the supercomputer.
Thinking about the cubic phase thing.
Yeah, just the cubic phase.
Okay, AutoCappa the cubic phase.
Yeah, just the cubic phase. Okay, it's coming along, but it's not finished, huh, Jayanta? Needs some more work. Okay. Oh, okay. Good job. Nicely done. Anything else? Okay, then. I'll see you guys.
See you.
Yeah,
Oh yeah. Oh, Kedar.
yeah,
Like we had Lester and Stephen and like Martin and I had a discussion. I think we want to share
yeah.
the compute responsibilities, and
Okay.
then like yeah,
Yeah.
that will. You had the I think you had the FHI IMS form like
Okay.
if you know, whenever you're ready. Yeah.
Yeah, yeah. Absolutely. Let me know what I need to do.
I think I sent you the form like
Send me the form.
yeah
FHI aims. I saw something. License agreement or something.
yeah.
I didn't sign it already.
Uh, Not yet. I think
Oh,
Volker is willing to provide it for free. I think
where do I sign, man? Okay, here.
right at the end.
I'm doing it now. Good thing you reminded me because
Yeah.
I would.
Then if you like do it if you do it like if you strike out the 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 price in the text, we could have the license for free. So
Okay.
Volker is offering fast.
Wow. Okay. I should just strike, or should I do that myself? Like strike out the price?
Yeah.
Okay. Where is the price? 2000 something something.
Yeah.
So I just strike it out. Is it?
Could like kind of change the text of it.
Why don't you do it? I'll send